Saxon's Trig lesson 12 on page 90 is about angles and diagonals and polygons and then proofs of the chord tangent theorem. They begin this lesson by showing you concave and convex polygons, and again, concave is one where you have a cave. And their point is not about the convex concave. So if, let me bring that one down here more. So if I have 5 vertices, 5 corners, dots in this shape, this one is concave because I formed a cave here. It's going to have 5 sides. It is the same if they are convex. So if this one came out, it's still going to have 5 dots, therefore 5 vertices to be precise. It's going to have 5 sides. Now, how many triangles can you draw from a convex polygon? And that would be one here and one here. Now, it doesn't matter where I choose to start. I can form 3 triangles. So a 5-sided shape is going to form 3 triangles. Every triangle is worth how many degrees? 180. So that means I'm going to do 180 times 3 to find out how many degrees are in this 5-sided or pentagonal polygon. So 540 degrees. So this will work for every single polygon. Find how many triangles will be in it and then multiply that by 180. Now, do you want to have to draw these every single time? You do not. So in general, the formula is the number of sides minus, so we went from 5 down to 3 by minusing 2. And it works that way every time. If you have an 8-sided shape, you're going to form minus 2, 6 triangles. So n minus 2 multiplying by 180 will get you the amount of degrees inside the triangle, or inside the polygon. What about the outsides? So if I extend each of these lines going the same direction around every time, this one plus this one plus this one plus this one plus this one all the way forms together basically a circle, and a circle is worth 360. So the exterior angles of the polygon will always total to 360, whether it has 5 sides, 10 sides, 100 sides. The total for the outside will always be 360 degrees. Then on page 92, that's where they give you, no, that's a different formula, the number of diagonals. Okay, so if I have a 5-sided shape again, and you want to know how many diagonals you can actually draw, which would be a diagonal is going from vertex to vertex across. Okay, so that's the same as forming the 3 triangles. However, I can start from here and create triangles here and here. And I can also create another one here. And so I have multiples going around, and it gets harder to draw them and then count them. So what we want is to take the number of sides, in this case 5, and then we will subtract 3 and divide by 2. And this is the formula. Oh, I'm sorry, I meant n. I was automatically filling in the 5. Formula is n with n minus 3 dividing by 2. So if we have 5 minus 3 is 2. So that's going to cut it down to 5. So let's see if that works out to the way we drew it. So in that first one, we had 3. In the next one, we formed 2 more. And with this last one, when I drew that line in, I formed 2 others. You can play with that yourself and actually do that count probably a little more easily than I can show you here in the video. But the formula works, and this is the formula for the number of diagonals. Example 1. Near the bottom of page 92 says, find the sum of the measures of the interior angles, and then in part B, the exterior angles of a 7-sided convex polygon. So we know we have 7 sides. The formula for interior said minus 2 and multiply that by 180. So that's 5 times 180, and that should be 900 degrees. So that's part A. And then in part B, it said what were the exteriors? No work involved. It's automatically 360 degrees. Not example 2. Now we move into part B, which is the proofs of the chord tangent theorem. All right, and that it's based on what we talked about before, which was that an inscribed angle has an arc that is double its amount. So for example 2, they want us to prove case 1. And so the 3 cases look like this. This one is a diameter type chord with its tangent. Case B is more an obtuse angle rather than a 90 degrees that's formed. And I should mark the center there. And the third case, again marking the center, is when I have an acute angle that is forming. And that's case 3. All right, so the first thing I would note in this proof is that I have a diameter and a tangent, therefore this must be 90 degrees. And I know that this is 180 degrees because it is half of the circle because it was cut by the diameter. So is it truthful to be able to say that this angle is half of this arced amount? Yes, it is valid. In example 3, it says prove case 2. Case 2 is based on case 1. So if you draw in this line to be the diameter, now it's basing on case 1. So it is this angle plus this extra little angle. Now they're going to go through with things, they've labeled it with letters, and so they're naming the actual angles and so forth. I wasn't going quite that far. So we know that this one is 90, this one is 180. Whatever this angle is half of this arc that is cut here. And so let's just say, for the sake of numbers, this is 20, then this will be 40. 180 plus 40 for the arcs is 220, and then 90 plus our 20 is 110. So is the arc double the angle that was cut? Yes, 110 doubles as 220. So case 2 works. Case 3, again, we want to base it on case 1, so we're going to draw that line in. So we have our 90 degrees for the full piece. And again, let's label this one 20 and this one 40. The arc that we're actually dealing with then is 90 minus the 20 at 70, and then sorry, I was debating, do you need to, yes, you do need to know what the other half of this is. And since the full thing would be 90 minus the 20 is 70, this part is the 70. So how much is its arc going to be? Double to 140. Or you could have said, if this forms 100, or if this is the diameter, then this whole thing has to be 180. So 180 minus 40 is 140. Either way, I get it. And so is it truthful then to say that 180 minus the 140 is 40? Yes. And is 40 double of the 20? Yes. So case 3 also works.